Good morning, everyone. Today's topic is the refraction of light. We'll look at the concepts of refraction of light and the simple optical instruments. Refraction is a phenomenon which occurs when light changes direction. It passes from one medium into another medium. Let us say we have a two media, air, and the medium 2, which is glass. A light may leave air and enter glass. Then when the light changes medium, its speed also changes and its direction changes. Then this phenomenon of changing the direction of light when light passes from one medium to another medium is called the refraction of light. Then here light goes through some things like air, glass, water, eyeball, and the presence of material in which the light travels slows the light, means reduces the speed of light due to interactions between light and the electrical properties of atoms of matter. Then the slowing factor of the speed of light is called the index of refraction. And this index of refraction is denoted by letter N, and the index of refraction for glass is 1.52, which means that light travels about 1.5 times slower in glass than in vacuum, where the index of refraction of vacuum is approximately 1. And the index of refraction of water 1.33, that of air 1.00028. Then in this phenomenon of refraction of light, we consider two media, medium 1 with index of refraction N1 and medium 2 with index of refraction N2. And the light leaves a light source in medium 1. Let us say we have a light source here in medium 1, and the light will leave the light source and it will strike the point of incidence at the surface of separation between the two media. This is called surface of separation of the two media. Surface of separation of the two media. Separation of the two media, medium 1 and medium 2, of two media. Then this means that this surface separates medium 1 and medium 2. Then when the light reaches the point of incidence, it changes its direction. Here we may determine the speed of light. Why the light ray changes direction? It's because when the light enters another medium, its speed changes. When the speed is calculated by considering the index of refraction equals to the speed of light in a vacuum, we divide by the speed of light in a given medium. Then N, which is index of refraction of the material, which means the slowing factor of light. Then where here the speed of light in vacuum equals 3 times 10 to the power 8 meter per second. Then this phenomenon of refraction may be explained by considering medium 1 to be denser or less dense than medium 2. Then here in this diagram 1, we have index of refraction 2 larger than index of refraction 1. This means that medium 2 is denser than medium 1. If medium 2 is denser than medium 1, the refracted ray approaches the normal. The refracted ray approaches the normal, while the incident ray goes away from the normal. This ray is incident ray, means a ray coming from the light source to the point of incidence. This is the incident ray, and this incident ray is away from the normal, and because medium 2 is denser than medium 1, and here we have a refracted ray. This ray is called the refracted ray. This refracted ray is approaching the normal because medium 2 is denser than medium refracted ray, is denser than medium 1. To be denser means that the index of refraction of medium 2 is larger than the index of refraction of medium 1. This means that when light reaches medium 2, the speed of light in medium 2 is very smaller than the speed of light in medium 1. If the medium is denser, medium 2 is denser than medium 1, then the speed of light in medium 2 is smaller than the speed of light in medium 1. Then, since the speed of light is very small, means it changes by decreasing, then it's the reason why the light ray approaches the normal. Then here in diagram 2, we have an index of refraction of the second medium is less than the index of refraction of medium 1. This means that medium 2 is less dense than medium 1. We have medium 2 here, medium 2, medium 2, and here we have medium 1. To have N2 less than N1 means that medium 2 is less dense than medium 1, which means that the index of which means that the light has a higher speed in medium 2 than in medium 1. It means the speed of light in medium 2 is larger than the speed of light in medium 1. This means that this angle of incidence is less than the angle of refraction, which means that the refracted ray goes away from the normal. This is our incident ray. The incident ray approaches the normal when medium 1 is denser than medium 2, and the refracted ray goes away from the normal. And here comes the law of refraction of light. We have two laws. The first law states that the incident ray, the refracted ray, and the normal all are in the same plane, which is called the plane of incidence. And the second law is the fundamental law of refraction of light, which is called Snell's law. This law states that in index of refraction of medium 1 times the sine of angle of incidence is equal to index of refraction of medium 2 times the sine of an angle of refraction. And in other way, sine of angle of incidence is equal divided by the sine of angle of refraction is equal to the speed of the light in medium 1 divided by the speed of light in medium. Then here we have an example of calculation. We have a laser beam which is directed upward from below the surface of a lake. We know that in a lake we have a water. So the beam of light, the laser light is in a lake. It is emitting light in air. Here we have an angle of incidence, and here we have an angle of refraction. We know that n1 sin theta 1 equals n2 sin theta 2. We are given the angle of incidence to be 35 degrees, and we are asked to determine the angle at which the light emerges in air. This is the angle of refraction. We are asked to determine this angle of refraction. Then it is given the index of refraction of air equals 1.003, and the index of refraction of water equals 1.33. Then here, index of n1 times sin theta 1 equals n2 sin theta 2. Then theta 1 is a question mark, and we get it as 49.7 degrees. Then consequence of refraction of light is the apparent death of a swimming pool. Here, if you drop, let us say, if you drop a coin to the bottom of a swimming pool, and you try to observe where your coin is positioned, the coin appears shallower, but and this S prime is what you call the apparent depth of the object in water, and S the real depth of an object in water. Then this is because of refraction of light, because if the body in water is at this position, then the light will leave this body and it will strike the surface of separation of water and air, and then the light will change direction according to the law of refraction, and the observer which is positioned here will think that she or he is seeing the object along a straight line and thinks that the object is shallower. The second consequence is that a pencil or a straw, a drinking straw in a glass of water looks bent due to light refraction. Then how fish are seen in water. If a fish is in a pond, then there is a light which comes from the fish at the bottom and reaches the point of incidence on the surface separating water and air, and the light is refracted into the eye of the observer. The eye of the observer thinks that he or she is observing the fish along a straight line and thinks that the fish is at this apparent depth, dA. But actually the fish is at a depth dr, which means the real depth, means the fish appears shallower than it is. Then total internal reflection. We consider the total internal reflection by first considering the normal reflection of light or refraction of light. Here, let us say a light leaves a light source in water, and the light will need to enter the air. Here, since index of refraction of air is less than index of refraction of water, when light reaches air, it will move faster than light is in water. Then this is the normal refraction. But then by increasing this angle of incidence theta 1 to a given angle in such that this refracted ray makes an angle of 90 degrees with the normal. Here we have the normal. This broken line is the normal to the plane. Then if the refracted ray makes an angle of 90 degrees with the normal, means theta 2 equals to 90 degrees, then this angle of incidence is called the critical angle of incidence. Then if we continue to increase this angle of incidence at an angle which is greater than the critical angle of incidence, then this angle of refraction will increase and become larger than 90 degrees. If this angle of refraction becomes larger than 90 degrees, and the refracted ray is directed in medium 1. Let us say here we have example of water. Then the angle of refraction becomes the angle of reflection, which means that we have a total internal reflection. This total internal reflection has two main uses. The first one, the use of fiber optics in medical diagnosis, especially the diagnosis of gastric ulcers, and in telecommunication. Let us start with the use of total internal reflection in telecommunication. Here we have a fiber optic. Then when signals, telecommunication signals enter the fiber optics, they are made in such a way the signals are striking the cladding at the surface of at the point of incidence, and then this ray, instead of moving out of this cladding, means this outer core, this outer part of the cable, the light ray reflects internally in the cable. Then this reflected ray becomes the second incident ray, and then it is also reflected internally in the cable, and then it becomes an incident ray, and then the reflection continues until the signal reaches the end point of the cable. This phenomenon is the same phenomenon which is applied in medical imaging, especially for the case of endoscopy, where medical doctors need to look in stomachs of patients in order to observe whether there are wounds in the stomachs or not. Then they insert this fiber optic into the throat, through the throat, and it enters the stomach and to the duodenum. Then the medical doctors start from the duodenum throughout the stomach to observe all sides of the stomach if there are wounds. Then the images of the inside of the stomach are incident into this cable or into this fiber, and then they reflect they reflect the incident again until the image is seen on a screen of a computer, and then the doctor may observe different wounds in the stomach. Then here we have an example of calculation. Determine the critical angle for both water and diamond with respect to air, where the index of refraction, the refraction of air is 1.003, that of water is 1.33. The index of diamond is 2.42. Here we need to use the formula sine of the critical angle equals n2 divided by n1. Then we need to calculate this critical angle equals the arc sine of n2 divided by 1 over n1 equals the arc sine of 1.003 over 1.33, because we are asked to find critical angle of both water with respect to air. Means the second medium is air and the first medium is water. And here the second medium is air, the first medium is diamond. Then we have such angles. Then the refraction through a rectangular glass block. Here we may consider a block of glass, and we consider two normal. The first normal is normal to the first surface, and we have a second normal to the second surface. First, a light ray leaves a light source in medium 1. Let us say medium 1 is air, and the medium 2 is glass, because the material we have here is a glass block. And the light ray leaves the light source and reaches the intersection between air and the glass at the point of incidence A. And then this light ray is refracted by approaching the normal, and here we have the refracted ray R. This refracted ray becomes the incident ray to the second point of incidence B, means the second incident ray to normal 2. Then here the light will leave the glass and then enter air. If since the index of refraction of glass is larger than the index of refraction of air, when light is emerging in air, it will move far away from normal 2. And if we do an experiment, we will see that this emergent ray, capital E, is parallel to the first incident ray. If we do the prolongation of the first incident ray, we'll see that it is parallel to this emergent ray. Then if we calculate this angle of incidence at the first point of incidence, is equal to the angle of emergence. And here we have an example. Light in air is incident on a glass block at an angle of 35 degrees. The sides of the glass block are parallel. We have here an angle theta 2 and angle theta 3. To answer to this question, angle theta 2 is equal to angle theta 3. And by definition, this angle of incidence 1 is equal to an angle of emergence. This means that theta 4 is equal to 35 degrees, but we need to show it by using Snell's law. Here we have n1 sine 35 equals to n2 sine theta 2. This is Snell's law. Then and n2 sine theta 3 equals n1 sine theta 4. Since n2 sine theta 2 is equal to n1 sine theta 4, then we'll see that n1 sine theta 3 sine 35 is equal to n1 sine theta 4. Then since n1 is the same, it will cancel each other. Then sine theta 4 equals to sine 35, then theta 4 equals to 35. Why do we say here n2 sine theta 2 equals to n1 sine theta 4? It's because the angle theta 3 is equal to angle theta 2. Any refraction in a triangular prism. A prism is a transparent and uniform material which is made of glass and bordered by two non-parallel plane surfaces, which is made of a pyramid. It has a shape of a pyramid. Then the prism has two effects on entering light. The two effects of prism on light. Of prism on light. The first one is the deviation of light. Deviation of light. Here, this means that when light is incident on a glass prism, the law of refraction of light is obeyed. This means that the light deviates inside the glass prism. Let me show it to you. Then in this diagram, here we have the incident light ray. It is incident at the first point of incidence O. Then this light ray is refracted inside the glass prism. This refracted ray plays a role of incident ray to the second point of incidence E. When the light reaches the interface between glass and air, the light ray will emerge along this emergent ray, and by making an angle of emergence E with normal 2. Then if we do the prolongation of this first incident ray and do the prolongation of this emergent ray, we will see that this incident ray and the emergent ray make an angle between them, and this angle is called an angle of deviation of the prism. Then this means that to say that the prism has an effect of deviating the light, this means that the incident ray is deviated by an angle of deviation D with respect to the emergent ray. The second effect of a glass prism on a light is dispersion of white light. Dispersion of white light means the separation of white light into a spectrum of 7 colors. Dispersion of white light. Then the dispersion of white light is the way when white light is incident on the glass prism, it first deviates within the prism, and at the point of emergence, this white light is separated into a spectrum of 7 colors: red, orange, yellow, green, blue, indigo, and violet. Then the way the white light is separated into colors is called the dispersion of white light by a glass prism. This dispersion of white light by glass prism has consequence of formation of rainbow. Then to have a rainbow, the sun shines when it is raining. When it is raining, still the sun shines. The water droplets in the atmosphere behave like a glass prism, and the sunlight travels always along a straight line. and the rays of light strike the water droplets. When the sunlight strikes the water droplets separates the sunlight into a spectrum of 7 colors of the rainbow. Then the combination of the spectrums of 7 colors, which are given by all water droplets in atmosphere, make a formation of a rainbow. Then the last point is lenses. Lenses are the main components in geometric optics because they are used in microscopes, cameras, telescopes, eyeglasses, and the human eye is also a lens. Then, let us detail them. There exist two types of lenses. There are what we call converging lenses, which may be meniscus, converging meniscus, plano convex, and double convex. The second type of lenses are diverging lenses, which have such shapes: meniscus, plano concave, and double concave. Then why some lenses are called converging lenses? It's because when we have a parallel beam of light from infinity, when it reaches a converging lens, the light rays after refraction meet at the same point, means they are converging to the same point. And for a diverging lens, when a parallel beam of light from infinity is incident on a diverging lens, or the refracted rays diverge, means diffuse in different directions. It's the reason why this type of lens is called a diverging lens. A lens has a focal distance. To plot the lens, we need also a pair of compasses, and these are two curves. Since they are two curves, they have a radius of curvature, and the half of the radius of curvature is called the focal distance, f, as described in reflection of light. And here the point which is located at a distance equaling the focal distance is called the focal point. And the lens has two focal points, focal point 1 and focal point 2. Here we follow with the image formation by thin lenses. There are rules to obey when plotting the images by thin lenses. Here we first plot our thin lens. We need to calculate the focal distance, and if the focal distance is well calculated, the point on the principal axis, which is at a distance equaling the focal distance, is called the focal point. Then the converging lens has two focal points. There is focal point 1 to the left of the lens, and a focal point 2, f2, which is to the right, or means on the other side of the lens. This is our lens. Then we also need to position the object. P means the position of object. We have an object PQ. And the first ray is said to be an incident ray, which is parallel to the principal axis. After refraction, it will pass through the second focal point. Rule number 2. An incident ray which is passing through the center of the lens doesn't change the direction after refraction. And rule number 3 states that an incident ray which passes through focal point number 1 after refraction in a lens, in converging lens, passes through a line parallel to the principal axis. The 3 refracted rays meet at the same point. Where they meet is the top of image. Then this is where the image is formed, image P prime Q prime. And this is the first incident ray. This is incident ray number 1, and this is refracted ray number 2. No, number 1. This is incident ray number 2, which passes through the center of the lens, doesn't change direction after refraction. This is the refracted ray number 2. And this is the incident ray number 3, which is incident by passing through the focal point 1, and after refraction it passes in a line parallel to the principal axis. Refracted ray number 1, refracted ray number 2, and refracted ray number 3 meet at a point after refraction. Where they meet is where the image is formed for the case of a converging lens. And this image is said to be real image. Image is real. Image is real. Real image because it is formed in the other side of the lens. When image is formed on the other side of the lens, the image is real. But if the image is formed on the same side as object, the image is virtual. And the second, the image here is diminished. Let us say the image is diminished. Diminished means smaller than object. If you look at the size of object and the size of image, you will see that this image has a smaller size than the object. And the third property of image is that the image is inverted. Image is upside down. It is not upright. It is inverted. Then we can continue with the image formed by a converging lens. We first plot our converging lens. We need to plot this principal axis which passes through the center of the lens. We need to position the focal point by putting it at a distance which is equal to the focal distance. The focal point 1 is on the right side of the lens, and we need to position focal point number 2, which is also equal to the same distance f, focal distance, from the lens. And the focal point 2 is on the left side of the lens. Then we position the object on the left side of the lens, and we continue with the rules. The first rule states that an incident ray 1 is parallel to the principal axis. When reflecting, it will appear to pass through the second focal point. Then it is refracted, appearing to pass through the second focal point. This is refracted ray number 1. Ray number 2 is a ray which is incident by passing through the center of curvature. This ray, after refraction, doesn't change direction, and this is refracted ray number 2. And the ray number 3 is a ray which would incident by passing through the first focal point. With this ray, when refracting, it passes in a line parallel to the principal axis. This is refracted ray number 3. You see that refracted ray number 1, refracted ray number 2, and refracted ray number 3 don't meet after refraction. Since they don't meet after refraction, we need to find their prolongation in the first medium. We do its prolongation of ray number 1, prolongation of ray number 2 in the first medium, prolongation of ray number 3 in the first medium. You see that the 3 rays meet at the same point in front of the lens, means to the left of the lens. Where they meet is where the image is formed. Then for any position of the object, for any size of an object, for the case of diverging lens, the image is always virtual. Image is always virtual. Image to be virtual means is in the same side as the object. Image is virtual means in the same side as the object. Image is always upright. Always upright in the same direction as the object. And the third property of image formed by a diverging lens, the image is diminished. Diminished means smaller than object. Diminished means smaller than object. Here we may look at the image formation by considering different positions of object. Here object O is outside the focal point at a distance which is almost twice the focal distance. The image is real. Here the first ray is a ray which is incident to the parallel to the principal axis in the refracting by passing through the second focal point. Ray number 2 is incident by passing through the center of the lens, and it doesn't change direction. Ray number 3 is a ray which is incident by passing through the focal point 1, and when refracting, it passes in a line parallel to the principal axis. Where the 3 rays meet is where the image is formed. Image is real, smaller than object, and inverted. Number B, object which is near the focal point 1. Here the first ray is incident parallel to the principal axis, refracted by passing through focal point 2. Ray number 2 is incident by passing through the center of the lens, and it doesn't change direction after refraction. Ray number 3 is incident by passing through focal point 1 and refracted in a line parallel to the principal axis. Here the image is real, and it is far away from the lens. Another point is in D, when object is at the focal point. If an object is at the focal point, we plot these rays. The first ray is incident parallel to the principal axis and refracted by passing through the second focal point. The second ray is a ray which is incident by passing through the center of the lens, and it is refracted in its same line. It doesn't change direction. We see that refracted ray number 1 and refracted ray number 2 are parallel, and the parallel rays meet at infinity. It's the reason why when an object is at the focal point, the image is located at infinity. Another special case is when an object is between the focal point and the lens. The first ray is a ray which is incident parallel to the principal axis and refracted by passing through focal point 2. A second ray is a ray which is incident by passing through the center of the lens and it doesn't change direction when refracting. You see that refracted ray number 1 and refracted ray number 2 don't meet after refraction. Since they don't meet and they are not parallel, we need to find their prolongation in the first medium. Then the prolongation of refracted ray number 1 and the prolongation of refracted ray number 2, they meet on the left side of the lens. Where they meet is where the image is formed. Then when an object is between the focal point and the lens, the image is virtual. To be virtual means that the image is located in the same side as the object, and the image is larger than the object, which means that image is magnified. This case is the same case that is used in simple microscopes and magnifying glass. A simple microscope and magnifying glass are converging lenses in which the object is positioned between the focal point and the lens. And here we have the thin lenses equations, which is similar to the equation for spherical mirrors, where the inverse of object position plus inverse of image position equals to inverse of the focal distance. And the magnification is equal to the size of image divided by the size of object equals minus image position over object position. And here we have a summary of properties of image formed by spherical lenses. Then for the case of converging lens, actually called the convex lens, the focal distance is always positive. Then when the object is positioned at position larger than 2 times the focal distance, the image is reduced and inverted and real. When the object is between focal distance and 2 times the focal distance, the image is real, larger than the object and inverted. And when the object is between the lens and the focal distance, the image is virtual and larger than the object. For the case of diverging lens, the focal distance is always negative, the position of object is always positive, the image is always virtual and smaller than the object. Then simple optical instruments. The first one is the human eye. The human eye has the crystalline lens. This crystalline lens has a shape of a converging lens. This means that the human eye operates optically as a thin converging lens. Then a normal eye must converge the images of objects on the retina. Then if this is an object, the images, the light rays come from an object and they reach the crystalline lens, and the lens refracts the image, refracts the object and forms images according to the refraction of light, and the image formed by a crystalline lens of the eye is being a converging lens. The image is inverted and smaller than the object formed on the fovea centralis, means on the retina. Then the human eye may have defects similar to other organs of the body. Then for the normal eye, the image is formed on the retina. Then there exist two main defects of eye. The first one is called myopia, where the eye is myopic eye or nearsighted eye. A nearsighted eye is an eye which focuses the images of objects in front of the retina. Then the images don't reach the retina. The second defect of eye is hyperopia, and the affected eye is called hyperopic eye or far-sighted eye. A far-sighted eye or a hyperopic eye is an eye which focuses the images behind the retina. And to solve the myopia and the hyperopia, first, for solving the farsightedness or hyperopia, there is a need of using converging lenses. Then a converging lens is given to a person who doesn't focus objects in just on the retina. Means those people who focus objects behind the retina. This is a disease which affects all the people. Then these old people, to focus things on the retina, they are given converging lenses. And to correct the farsightedness or myopia or a myopic eye, a diverging lens is needed. Then for people who focus objects in front of the retina, a diverging lens is prescribed to them. This is a disease which affects middle-aged people and young people. The second instrument is the camera. The camera uses also a converging lens, and the images formed by this lens of the camera are smaller than the object and inverted, and the image will come out of the camera being upright according to the electromagnetic circuits which are inside the camera. And the third instrument is the magnifier or magnifying glass. This is a converging lens where the object is positioned between the focal point and the lens in order to increase the size of the object. The magnifying glass operates in a similar way as the simple microscope, which is used at health centers and hospitals in order to observe different diseases in our blood and body. The fourth one is a compound microscope. A compound microscope is an optical instrument which is made of two converging lenses. The first converging lens is called the objective lens. Another one is called the eyepiece lens. The eyepiece is near the eye of observer, and the objective lens is is near the object. The objective lens has a focal distance which is less than the focal distance of an eyepiece. The fifth one is an astronomical telescope. An astronomical telescope is also consisting of two converging lenses, an objective and an eyepiece. And then in order to observe objects at infinity, means very far objects, the objective must have a larger focal distance compared to the focal distance of the eyepiece. Then the difference between compound microscope and the astronomical telescope is that for compound microscope, the objective has a smaller focal distance compared to the eyepiece. Then for the case of astronomical telescope, the objective length has a larger focal distance compared to the eyepiece. And the last instrument is the reflecting telescope, which uses concave mirrors or plane mirrors in order to observe very far objects, and this is the most preferred telescope in astronomy. It is negative and it is equal to -9 centimeter. Since Q2 is negative, this means that the final image, formed by lens number 2, is a virtual image, which means that this image is located to the left of lens 2 at 9 centimeters. And the final magnification is equal to magnification 1 times magnification 2. We know that magnification equals minus Q1 over P1 times minus Q2 over P2. All these numbers are calculated. We have magnification equal minus 0.6. This means that the final image size is equal to the size of object times the magnification. Then the size of image is 0.9 centimeter, smaller than the object. Question number 2. A stamp collector uses a converging lens with focal length 24 centimeter to view a stamp 18 centimeter in front of the lens. Where is the image located? We are asked to find the location of image, means the position of image. Given P, no, this is the focal length 24 centimeter F, and the position of object 18 centimeter P. Then 1 over object position plus 1 over image position equals 1 over focal distance. Then 1 over 18 centimeter plus 1 over the eye is equal to 1 over 24 centimeter. Then the image position is equal to minus 72 centimeter. To have an image, the position of image to be negative, this means that the image is virtual. The image is virtual means that it is positioned on the left side of the converging lens, which means that image is in the same side as the object. B, we are asked to find the magnification. Magnification equals minus position of image divided by position of object. Minus 72 centimeter over 18 centimeter equals plus 4. To have a magnification of plus 4, this means that image is larger than object by a size of image is 4 times the size of object. Means that the size of image is larger than the size of object by a factor of 4. Then we are ending refraction of light. The next are practical activities. Thank you very much for watching.